Hey everyone, welcome back. In this video, we're going to talk about how to graph polynomial functions. In some of our previous videos, we've seen how to graph certain types of polynomial functions. In particular, we've seen how to graph linear functions, quadratic functions, and even transformations of our cubic functions or third-degree polynomials. And now we're going to approach how to graph larger polynomials of degree 4 or more. And what's going to be nice is that we can really recycle or reuse a lot of our knowledge about linear, quadratic, and cubic functions to help us. So in order to graph our polynomial functions, and this is really going to apply to graphing almost any function, we're going to need to know the end behavior or the long run behavior of the function. And we're also going to need to know the short run behavior or the short term or local behavior of a function. And so it doesn't really matter if we start our discussion with that short-term or long-term behavior. I'm going to go ahead and first start by discussing the end behavior or long-run behavior of our polynomial functions. So we'll be looking at and analyzing our polynomial functions in several different forms throughout all of our videos. In particular, there's going to be two forms that we use most often. That's going to be our expanded form, which we see up here and how we usually first define a polynomial, and then also the factored form of a polynomial. Each form has some advantages and disadvantages that make certain pieces of information about our polynomial functions easier to identify. And depending on which piece of information we're looking for, we might work with a certain form of our polynomial. So when it comes to finding the end behavior of our polynomial, usually the expanded version of our polynomial is going to be the preferred form to work with. And the reason for that is the end behavior of our polynomial is determined completely by the leading term of our polynomial. So remember, when our polynomial is in that expanded form, the leading term is just the largest power of our variable that shows up in our polynomial and includes the coefficient that power of our variable is multiplied by. So if this was our expanded form here, the leading term, that very first term or the largest term, would be a sub n times x to the power of n. Remember, the end behavior or long-run behavior of a polynomial is really just trying to determine what happens to our function when x gets really, really large or when x gets really, really small. And by small, we actually mean really, really large but negative. So we can also phrase that as what happens to the outputs of our function as x approaches positive infinity or moves off to the right, or as x approaches negative infinity and moves off towards the left. Well, what ends up happening once x gets sufficiently large enough or big enough, either positive or negative, is all these smaller powers of x really become insignificant and contribute almost nothing when compared to the leading term, right? We're talking about really huge values of x here, like 1 million, 1 billion, or even way larger than that. And if we just compared like 1 billion to 1 billion squared, well, 1 billion is a big number, but not when compared to 1 billion squared, so it becomes insignificant. So the long run behavior, the end behavior of our polynomials all come down to the leading terms. And well, we have infinitely many different types of polynomials, which may seem intimidating, but when it comes to the end behavior, there's really only 4 cases that we have to remember. And to help us remember these 4 different cases, we really just have to refer back to what we already know about our quadratic and cubic or linear functions. And so we're really going to break our polynomial functions into kind of 2 groups, what we call even polynomials and odd polynomials. And here when we're referring to the even or oddness of a polynomial, we're really just referring to the even or oddness of that leading term, the one that determines the end behavior of our function. So if we have an even degree for our leading term, so an even degree is just like an even number, so like 2, 4, 6, and 8, then the type of end behavior we're going to encounter for that even degree polynomial function, or really even degree leading term polynomial function, is going to look like the end behavior for a quadratic function. So remember, our quadratic functions can either be concave up or they can be concave down. And so these are our 2 cases for when our leading term, remember we're ignoring all the other terms, but our leading term has an even degree. So it could be an x squared, which is a quadratic that we've already seen before, or it could be an x to the 4th, x to the 6th, x to the 8th, and so on type leading term. And how we determine whether the end behaviors of our polynomial function are going to be going up as we head to the left or right, or down as we head to the left or right, is the same way that we did for our quadratic functions, in that it comes down to also knowing the sign of that leading coefficient. So is that number that our leading term multiplied by positive or negative? Remember, we're calling our leading coefficient in general a sub n. Well, if a sub n is positive, then the end behavior of our polynomial function with an even degree leading term is also going to be positive in both directions, meaning as we head to the left, we're going up, or as we head to the right, we are going up. And so if our leading coefficient, a sub n, is less than 0 or negative, that's when we're going to have the end behavior where we go down as we move to the left or to the right. And so I've drawn some complete quadratic functions here for these little examples, but remember, we're really just describing the end behavior of these functions, what's happening to the far left and far right on our graphs or to the outputs of our functions. It's probably more accurate now to actually erase the middle parts, because what happens in between the end behaviors is going to depend a lot more on those other pieces that we are ignoring for now. All right, so our first two sets of end behavior kind of started with looking at even degree leading term polynomials. The second set of our end behaviors are, of course, going to then look at odd degree leading term polynomials. Well, to help us remember the end behavior for our odd degree polynomial functions, we just have to remember our cubic function. And so this is what our standard y equals x cubed graph looks like without any transformations. And then, of course, just like for our even degree polynomials, we could vertically reflect it or flip our end behaviors over. So for odd degree polynomial functions, if we head off to the left and go down towards negative infinity and head off to the right while going up towards positive infinity for y, that's only going to happen when we have an odd degree and a positive leading coefficient. And well, we'll get our last set of end behavior going up as we move to the left and down as we move to the right when we have an odd degree leading term and our leading coefficient, that number a sub n, is negative or less than 0. So again, remember, just like for our even degree polynomials, same with these odd degree polynomials or odd leading term degree polynomials, the end behavior is only describing what happens to the far left or to the far right, or when our inputs and outputs get extremely small or extremely large. So a couple final thoughts on the end behavior of our polynomial functions and things to remember are, remember, this discussion we've had is assuming that our polynomial function is in this expanded form, so we can quickly and easily identify our leading term to determine the end behavior. And so what happens if our polynomial is not in this expanded form, but maybe it's in like a factored form? Well, then what we have to do is take our factored form and expand it, or at least expand it far enough to identify what the leading term would be. So one last note to make about end behavior for polynomials, and maybe this is more of a personal note for the type of notation I like to use. This probably isn't very rigorous or widely used notation in mathematics, but if I'm describing the end behavior of a polynomial or really a function, when it comes to graphing, I might make a couple notes to help me remember what the end behavior is. So for this first case, I've described the end behavior using a coordinate pair like this, where I have an arrow that is pointing up and to the left, describing the left end behavior, and an arrow that is pointing up and slightly to the right for the right end behavior. Right? We can do this for all four cases here. So for the even degree leading term case, where our leading coefficient is negative, we should have two arrows going down and to the left and down and to the right for helping us describe our end behavior. And for our odd cases over here, we should have down and to the left for the first case and up and to the right for the second. And for our second case, for the odd degree cases, when we have that odd degree leading term and a negative coefficient, well, as we move to the left, we got to go up. So we're left and up, and then down and right. So I just wanted to make sure that I mentioned this little notation because I'll probably be using it in some later examples. Welcome back, everyone. I want to do a quick example of looking at some polynomial functions in either expanded or factored form and very quickly identifying the end behavior of that polynomial function. So the first function that we are trying to find the end behavior of is this polynomial function f of x here in part A. It's defined as 5 plus 4x squared minus 3x cubed. And remember, if we want to find the end behavior of a polynomial, it all comes down to the leading term of that polynomial. So the leading term is not necessarily the first term we see or the farthest term on the left. might be written in some random order. We have to identify the leading term by finding that highest power of our variable. So our variable here is x. The highest power that shows up is at the far right here in x cubed. So our leading term is negative 3x cubed. We can see that we have an odd degree polynomial. So that'll put us into one of our two cases to the far right over here. And we have a negative lead coefficient. So it's like the end behavior is an x cubed graph's end behavior, but then vertically reflected. So that's this case over here. Our end behavior for our polynomial function in part A, the one we're calling f of x, is going to go up as we move to the left and down as we move to the right. And so we have to be a little bit more careful when we're trying to find the end behavior of our polynomial g of x in part B, because our polynomial g of x is not written in its expanded form, it's written in a partially factored form. And so if we look at our polynomial in its partially factored form, we see that the largest piece is that x to the fifth piece, but x to the fifth piece on its own is not the leading term of our polynomial, right? The leading term is really identified from that expanded form, and it's got to be that largest power of x and the coefficient involved. And so what that means is that we're going to have to expand our function g of x, but we don't actually need to do a full expansion and do all the distribution to find the leading term. And so the way we find the leading term of a polynomial in its factored form is we expand it. We don't have to do a full expansion, only a partial expansion. We look at each factor, identify the largest piece or the leading term of each factor, and then multiply all of those together. The idea is if we were to do all the distribution, expand everything out as much as possible, well, how would we create the largest powers of x? They'd only be created when those largest powers of x were being multiplied together through the distributive property. So that's a long-winded way of saying just take the biggest pieces from each factor, multiply those together, and that'll give you your leading term. We don't need all those other pieces here. Our negative 5x times x to the fifth, if we multiply those together, that'll actually give us negative 5 times x to the sixth. That would be the leading term of our polynomial g of x here. And so we can see that that power is an even power because of that 6, and we have a negative leading coefficient. So we are in our second case here, where the end behavior would resemble that of a concave down quadratic, meaning that we are going to be going down as we move to the left or as we move to the right on our graph.